All right, welcome to the next in the series showcase on online teaching in the science lab area, this one on chemistry. I have the great privilege of having two presenters today. Mark Blaser has a BA in chemistry and mathematics from Carleton College and an MS in chemistry from the University of Colorado. He has taught at Shasta College for over 20 years, primarily general chemistry. His current focus is on developing, implementing, and improving research-based, student-centered instructional approaches in chemistry courses. And he is a principal investigator on the California Education Learning Lab grant, which is called Improving Learning Outcomes for All General Chemistry Students Through Adaptive Hybrid Courses. Our other presenter is Nick DeMello. Nick teaches fully online general chem at Cañada College, where he is also the campus DE coordinator. Nick's Design for Teaching teams won top prize in the statewide Reimagine Online Learning Challenge launched by California Community College's Chancellor's Office in 2019. Nick received his BS in chemistry from UC Berkeley and PhD in synthetic organic chemistry from the University of Pittsburgh. After a postdoc at UCLA, Nick helped establish the UCLA Center for Digital Innovation. All right, we welcome Nick and Mark, and why don't we start with Mark, who has been busy collecting resources that instructors may be able to use in online science lab courses. Mark, take it away.
Okay, hi everybody. Thanks for joining us. I'm just going to note for starters that I'm participating not as an expert on online labs, but as somebody who's done some online labs, tried out various things, like many of you, has been forced into online labs rather quickly and is working for a better solution for online labs in the fall. And I'm going to share the screen. And I will also note that, oops, get started here. There we go. So this is going to be kind of a quick survey. I'm happy to have questions, but I'm mindful of the available time. So this isn't going to go into tremendous detail, but I'm going to look at 5 different online lab, I'm going to call them partial solutions. One is Labster simulations. Another is ChemLabs simulations that are part of the InSpark learning network and hosted by Smart Sparrow. VLabs virtual labs, which are part of the Chem Collective that was started by Dave Yaron at Carnegie Mellon University and that are incorporated into the Open Learning Initiative General Chemistry courseware. Some simulation-based activities, I'll just brush on that because I know Nick's going to talk about that a bit. And then homemade lab videos, and probably just a very short amount of time on each one, at least for starters. So myself myself and some colleagues at Shasta College have used some Labster simulations during the move online in the pandemic response. We had an innovation grant to explore these previous to this, so this was a thing we were going to do anyway. There's a whole bunch of simulations. They all start with this sort of virtual reality futuristic city. There's a little bit of an introduction, what the lab's about, what the learning objectives are, so a little bit of what you're in for. There's, generally speaking, a sort of real life scenario, relatively corny introduction with some virtual characters. So here, this is ending up being an introduction to acids and bases via diet and dietary effects and how that might pertain to acids and bases. And then you're given instructions, some background, some resources via what they call lab pad. So this is information that you refer to. And then there's a holotable where you can look at some models of molecules. And there are some virtual lab benches where you can do things like pour solutions, measure their pH, with your virtual disembodied hand doing the work. And then you interact in various ways. So here you're being asked to use different solutions and relate hydrogen ion concentration to pH and establish the relationship with that between those. And then you get some questions and you get a score and feedback along the way if you either are getting things right or if you're not. Very quickly, sort of my version of pros and cons. They have a lot of simulations on a lot of topics, not just chemistry, but biology, physiology, etc. They're fairly engaging and fairly active for the students. They do vary a lot, but there is definitely engagement. They're adding labs, they're updating and grading and upgrading their labs, and they're fixing errors, and they do have some errors. A lot of computing power is needed, at least relative to maybe what all students have. And because of this, the simulation can freeze, students can get stuck, and that can be quite frustrating to students. We found we really have to vet the simulation for appropriateness. It's really hard to tell ahead of time if it's going to do anything like what you think it should do based on the topic. And you're probably going to need to support students as they go through it, or they're going to get stuck, get frustrated, and give up. And they are generally a little bit on the pricey side, but they have been free in current situation. Okay, and I'm just going to kind of keep going unless I get interrupted, Bob, by a question.
Yeah, they asked, I'm going to answer the Labster LTI question, but do they offer organic chemistry?
There are some organic chemistry simulations. My organic chemistry colleague at Shasta College found them pretty limited, but they are adding more, and we were told there would be more by kind of the end of this spring. Definitely as of mid-spring or as of recently, not enough for a full-on organic simulation or a lab experience, but they do have some and they're adding to it.
Very good, thank you.
Okay. So next one is ChemLabs. They were developed by Mike Lerner at Oregon State University. They're currently hosted on the InSpark network and use the Smart Sparrow program. And it's a virtual laboratory where you have beakers and flasks and you can get supplies. And it's pretty much here's some instructions, an introduction to the lab. So this one happens to be an iodine clock reaction between hydrogen peroxide and iodide ion. And you have some instructions. You have a table in this particular case of various solutions, amounts you're going to pipette into the flasks that'll then be mixed. And students are expected to keep their own records on what they pipetted, and it checks whether you did it properly or not. So you have a virtual pipette, which you can drag over a beaker, withdraw a given amount of given volume of solution, and then dispense that. So it kind of goes this little vivid or fluorescent blue color to show that the pipette has docked over the flask. You dispense your fluid, you do it on the other flask, and so now you have your two flasks that are going to be mixed together. And then when you mix these two flasks together in this particular lab, a timer starts, and then the student watches for the color change to occur and stops the timer when that happens. And then they do some calculations, in this case, some graphing, and answer some questions. And so you're kind of simulating a lab, a version of a lab that maybe many of us would do in a Gen Chem 2 class. Gives feedback, and it does auto grade things as well. Some pros and cons on this. There's 2 semesters of general chemistry labs, so it's nominally enough for a full sequence. They also have prep chem as well, and the InSpark platform also has a sort of more liberal arts chemistry course called Critical Chemistry. Pretty good coverage of the usual experiments. I found them to be quite accurate and error-free, and the students actually are, in a virtual sense, doing the experiment. They're pipetting out volumes, they're mixing them together, they're observing when the color change occurs, etc. The cost, they're free at the moment, but normally it's $6 per lab per student with a discount for more than 3 and a maximum cost. And I have found that my less independent students kind of bog down sometimes, and without support, they end up not finishing or getting a really low score. The more independent learners, the more tenacious ones, the instructions are, well, should I say the ones who read and follow directions tend to do fine with this. And pause for questions, if any, or move on.
Yeah, there's, I think you answered most of them, but somebody asked if you also checked into Beyond Labs as a resource.
I did not.
Okay. And if those of you who are listening or watching, if you have some feedback on that, feel free to share it in the chat. Question, did you find any lab simulations for introductory level chemistry in Labster or any other package? And I think the answer is yes to that, right?
I would say yes to both of the ones I've talked about so far, Labster and ChemLabs. Probably introductory chemistry, the critical chem would be more appropriate on the Smart Sparrow platform.
Yeah. A couple other questions about cost. The $50 maximum for a course or for a student?
Student.
Okay.
Per course. So if you as an instructor picked, I don't know, 12 labs, that would be $72. No, it's capped at 50.
Okay. And how long will it be free, did you say, ChemLabs?
I believe through the summer for sure. Don't know about fall. So some of these are things that would, I think, are their moving target.
Got it. Thank you.
Sure. Okay. The next one is VLabs, or virtual labs, out of the Chem Collective, which is kind of combined with the Open Learning Initiative at Carnegie Mellon. The Open Learning Initiative chemistry courseware has actually been made free for COVID impacted institutions. Again, I believe through the summer, not sure about the fall, and I'll mention another thing about that in a bit. Excuse me, the virtual lab itself looks kind of like the previous, the ChemLabs. It's the same essential idea, but it's got a little different look. I'm just going to show you a fairly simple specific heat of a coolant virtual lab using this platform, and this happens to be embedded in the general chemistry courseware, the OLI courseware. So there's a little problem. You're designing engine coolants and you're looking at heat dissipation, and you have water, you have this compound that you're testing. Of course, you have access to flasks and beakers and graduated cylinders and pipettes, etc. But in this simple case, what you can do is you can dispense a amount of water, and there's a realistic mode. You just sort of push, hold down, and it pours, and you get kind of a random amount. You can also set it, if you're using a burette or a pipette, to an exact amount. And then it'll show how much volume has been transferred. So now I have a beaker with 94.52 milliliters of water, and I can heat it up and insulate it from the surroundings. So now I have some higher temperature water. And then I have some, and it shows me the amount of water, the temperature of the water, and it shows the temperature also on the side. And then I have a lower temperature solution, or sorry, compound that I'd like to find out something about its thermal properties. And so I'm not showing the mixing process, but I docked them and they were mixed. And so now we have a total solution volume of the two. The compound Y is now empty, and the temperature goes to a in-between temperature. And then based upon that data, students are asked to find the specific heat of this compound. And that's just an example, but of course you can do, reactions of aqueous solutions, you can do, titrations, you can do dilutions, etc. Kind of on this platform. Pros and cons of this: there are already a fair number of written labs, and the platform can be used to develop new labs. They're pretty scientifically accurate and representative, but you can't right now at least do all types of labs. So for example, there's not a way to do kinetics labs within VLabs as it currently stands, but that's a doable thing. And I will just note the project that I'm part of, a group of instructors will be working on developing hopefully a complete set of Gen Chem labs using this platform that we're willing to share.
Mark, question: do ChemLabs and VLabs experiments come with a module with pre-lab procedure, post-lab discussion questions?
The ChemLabs, the way they're set up, they have an introduction and then a procedure and then an analysis section. And that's sort of the instructions on the right side with the lab, the lab tabletop, virtual lab on the left side. The VLabs are pretty much, it's a platform for doing experiments, and the written labs are in various stages. I guess what I would say in general is they're just a lab to do a specific thing, but an instructor could build a pre-lab easily using this. Am I answering the question? Very
good. Which of these virtual lab resources have OChem, I assume organic chemistry?
The last two that I did do not really have organic, I believe. And I should note I'm kind of a denizen of the Gen Chem world, so I'm less able to comment on organic chemistry.
Okay. Kelly shares that Beyond Labs does have OChem and great for 200 level. All right, very good. Please continue.
Okay. And I think I'll be able to finish up fairly quickly. I'm just going to drop in a shameless plug here. But the project I'm working on, we're collaborating with the Open Learning Initiative and their general chemistry courseware. And because of the transition to online instruction for the fall, we're now also going to be developing some online labs. This is specifically for general chemistry. And we have a nice little consortium of colleges. It's somewhat community college focused, but not exclusively. And I guess anybody, we're willing to share, anybody who is interested in either learning more or participating at some level, just contact me. So last two things will be, I think, pretty quick. I'm just going to mention simulation-based activities. I know Nick is doing more with this, but for a number of years now, I've been using specifically PhET simulation-based activities. I'll mention two. One is a molecular shapes and polarity lab activity. It's not a true wet lab. And so they have a molecular shape simulation. They have a polarity, actually two molecular shape simulation, a polarity one. And students can explore and interact with molecules and interact with them in electric fields in ways you just could not do in a standard lab. And the other one that we have used quite a bit is a hydrogen atom spectrum, and do a kind of deep dive into the analysis of that, again, in a way you can't really do with just discharge tubes and putting salts into Bunsen burner flames. And so the simulation-based activities let you do things that you can't really do in a physical lab. The reason I do them is to kind of do a deeper dive into conceptual understanding for students, and sometimes calculational as well. Students get really engaged with these, but not all chemistry instructors are happy with things that aren't a standard wet lab if you're doing it during lab time, because the students aren't learning techniques. And that doesn't bother me tremendously if that's not all you do, but that is an objection some people make. And I know Nick's doing more on this as well.
Very good. Mark, do you know what your colleagues at UC and CSU are using in the way of online resources?
Mixed bag, and I'll address that a little in about 2 minutes when I'm just about done.
Oh, very good. Let me scroll down here. Is FET all Flash or some HTML?
FET is trying hard to convert everything to HTML5. They still have some Java-based. I don't know what the proportion is, how many are HTML5 now and how many are still Java, but that is a bit of an issue. Some of them are in kind of old technology.
Right. Okay, we're caught up.
Okay. So the last one I'm going to mention is actually what I think most colleagues that I've talked to have done, at least in this sudden response, is homemade lab videos. So this one, I got the appropriate chemicals from our stockroom, and on our kitchen counter, we did a solvolysis reaction of tert-butyl chloride, and students were determining activation energy from determining reaction speed at some different temperatures. So you literally video the lab, show the students what they would have done, and how long it takes for the color to change, and then the students do a lab report in kind of the standard way. And I did a few of those this spring. Colleagues of mine have done quite a bit of that. Nice thing is you're doing something that's customized to what, these are labs that you already were going to do. There's an advantage in that you're doing what you're used to doing and you don't have to rethink things as much. There's a disadvantage in that you're doing what you're used to doing and you're not having to rethink things very much. And students are doing an awful lot of observing rather than doing. They're not measuring things out themselves. They're not interacting with stuff, at least if you just kind of quickly create a video. And they take some time to create, maybe some support because you have to have access to campus and the chemicals. I mean, I think it's okay in an emergency. I'm not thinking this is a generally great solution, even though lots of people have been doing that. Again, my opinion at the moment. So almost done. What's the solution? Because of course, chemists have all the solutions. And I don't think there's one solution. Probably the solution is a mixture of solutions with several bad embedded chemistry puns in there. I think with time to think things through and prepare, we definitely need to think about what we're doing and why, what are the learning objectives, which type of approach best is best for a given situation. And I think we certainly need to evaluate and assess how well these things work in terms of student learning. And boy, sharing the load with some other instructors would help a lot. And that's probably the main reason I'm participating in this, is not because I've got tons of answers, but because I would sure like to work with other people on solutions. And that is it for me.
All right, thank you, Mark. We have a question for you and everyone. Has anyone investigated the virtual chem labs at Davidson College, authored by David Blauch, B-L-A-U-C-H? If you have, feel free to type in the chat. Okay, if you do have more questions for Mark, feel free to type them in chat, but let's now hand the baton to Nick, who will elaborate a little more on those resources, and I think he's going to show us a tour of what he's done. Take it away.
Hi, so my name's Nick DeMello. Do you guys see me in the speaker view at this point?
If I click speaker view, I can. Otherwise, you're in a small screen.
in the upper right-hand corner, please click on the speaker view so you can see me in the big picture as opposed to the tile. Like Mark said, I'm not here to provide answers. I think the best teachers don't give you answers. They kind of point you to solutions. I'm going to try and share with you some of the things that we've tried to do, some of the things that we thought were important and some of the solutions we've come up with. Now, the idea here is not to do a lab course online. The idea here is to support a course that has a lab component in this new online world. And so I think a central question to that is, why are we doing the experiments in the first place? And this is kind of where we started from. Why are we doing these experiments? What is the underlying value of doing the experiments? We didn't try and just translate our classes online. We tried to rebuild them in an online environment. And so the idea is, what are the underlying objectives? And I think there's a lot of reasons to do a course online. There's things like, there's a lot of reasons to do experiments. One is the discovery aspect. Students learn more when they discover something as opposed to just handing it to them. Demonstration of chemical principles, exploring limits, content retention. I'm going to try and hit on all these keys as I go through. There's 4 solutions that we came up with. One is kitchen-safe chemistry. Another is doing real experiments with virtual equipment. Another is take-home lab kits. And the last is remote participation. And I'll tell you right now, the remote participation is something we're just getting started with, just starting to explore. The first solution in context of our class starts in Canvas, and we have the content broken out into different divisions. As students break into each of the divisions, they go through a study cycle each week. We tell them in advance we're going to put the objectives up front. We're going to ask them to do some background reading. Then we're going to engage with them in adaptive learning and other methods. And the experimentation is a key part to that because it makes real a lot of the things that they are trying to explore. The first thing we tried in accomplishing these things was kitchen-safe chemistry. I think a lot of you guys have done the same thing. In terms of what I mean by kitchen-safe chemistry is the chemistry is all around us. I mean, we tell our students that all the time. We don't necessarily need to use hydrochloric acid and sodium hydroxide to demonstrate acid-base chemistry. Similarly, we can show kinetics in a shot class. We can. There's a lot of things that we can do around us to explore, and there will be some equipment. There are some pieces that we weren't able to build or tell students they could pick up through their drugstore or at home. A good source for those is these is home science tools. When you need some extra materials, when you need a small kit, you can pick up pieces, or you can build your own lab kit, or you can send students to it to build their own lab kit through home science tools. There's chemicals. There's different instruments you can pick up and glassware. I wouldn't go there. I mean, in addition to that, they offer full lab kits and experiment kits. We had. I'll talk more about full kits in the next piece, but this was our kind of build your own solution. The next piece was virtual equipment. And again, if you're trying to do discovery, if you're trying to figure out what's going on in where you're trying to explore these different systems, the key is to observe, to be able to try things, to be able to make mistakes, and to see the consequence. We've been using virtual experiments that we crafted ourselves where we set up experimental procedures. We wrote out the description for it. We challenged students to work with equipment. The difference is the equipment wasn't something that they came into a laboratory and put their hands on. Instead, it was software. And this is different than just a simulated experience. This is different than just going through a scripted environment. This is a chance to make mistakes, to work with the equipment, to see the consequences of it. And yes, it is a computer simulation. It is reproducing the effects of things in the real world, but it's free form, and it gives them a chance to work with the equipment, see the underlying relationships. One of the places that we went to get virtual equipment, and there's lots of equipment all over the place. The Merlot system is one place where you can find all kinds of different systems. Another one is FET. I put the FET link in the list earlier. One of the advantages of these systems is you can find different pieces of equipment that different folks have produced. You can embed that in your laboratory. And for example, this lab that explores molecular shape and polarity uses 3 different FET simulations. The previous one uses 2 different FET simulations. You can have an A part and a B part. You can lead them through a more robust discovery process. All right, so those are the first 2 pieces. Any questions about simulations? Yeah, Merlot is a good resource. As a disclaimer, Merlot doesn't actually host or collect or build this stuff. Rather, Merlot works with a federal grant to basically provide you links to various sources all over the internet. But you can go there and you can read about them and connect out.
Hey, Nick.
Yes?
Got 3 questions here for you. An earlier one I missed was, my issue with simulations, they tend to be too foolproof. Students learn by making mistakes. Do you feel any of these platforms, resources are better in regard to requiring the student to be seriously engaged in the process?
Yeah, I mean, the ones where you basically just push a button and see the results, I tend to avoid, and there are a lot of them out there. There are other ones where you can adjust the parameters. You know, Mark was talking about some of the VLabs experiments where you can mix different materials and see the consequences. You can get a wrong result. You can put you can forget to put the indicator in your titration, and you'll never see a color change. I absolutely agree that we learn from making mistakes, and some of the best advantages in some of the best opportunities in the lab is the opportunity to make mistakes and therefore learn from the experience. There are some systems that are a little bit more storytelling. They're more about leading you through a process, and that has value too. But I would differentiate between those and real experiments with virtual equipment precisely because they allow you to make mistakes.
Okay. Another question had to do with liability. Is there a liability for instructors if something goes wrong at home, at the student's home with a kit in any shape or form?
Yeah, I'll talk a little bit more about liability when I get to the lab kits, the pre-built ones. With regard to kitchen safe experiments, the first priority there is safety. I mean, you know, I tell folks that the chemistry lab is the single most dangerous place on campus, and my justification for that is the insurance premiums we pay. Bottom line is chemistry is about changing matter, and students matter. So there's risk involved in that. However, for take-home kits, for kits where students are putting together things on their own, I strongly encourage thinking about the materials and using relatively simple materials so that you minimize any potential risk. Also, microscale or small scale experiments really takes out a lot of the more dangerous aspects you run into in a full-blown university chemistry lab.
Thank you. Another question had to do with cost. Were you lucky enough to have your college pick up the cost of any of the kits you might be using?
So again, I haven't talked about the kits yet, but yeah, I was able to, with the home experiment stuff, that's stuff that we can either fund through the department and put together and be able to hand out, or more frequently for experiments, because as Mark said, you know, the results are really a little bit of this and a little bit of that. You can ask students to collect things, make it, you know, the first part of that class to be a little bit of a hunt to get to build things. And in that case, the students are paying for the stuff out of the grocery store. But again, those materials have a very small cost. The kit, if we start using more professional equipment, that becomes more of a challenge. Another thing you can do is you can make an A-B kit. You can make it an A kit that is consumables that, that students are going to have to restock or repurchase, and then a B kit that can either be loaned or rented that is more instrumentation and glassware. And you do have to charge a fee for that because there will be some breakage and some stuff won't get returned. But by splitting it into an A-B half, you reduce the overall cost associated with it.
Okay, thanks, Nick.
Okay, so now I would like to differentiate from the kitchen safe stuff, which is kind of a build your own model, to take home lab kits. The motivation for the take home lab kits is the demonstration. You can discover a lot of things in simulation, but, and someone was asking about organic earlier. With regard to the simulations on organic, I'd encourage folks to take a look at a company called Wave Function in Southern California. They are they make semi-empirical packages that can do, you can actually explore reaction mechanisms with great detail. And they've got some educational resources there as well. So if you're trying to illustrate, you know, chemical reactions, in terms of simulation, Wave Function, Warren Harry, who used to work at UC Irvine, the URL is, haven't talked to these guys in a couple of years, but they had some awesome solutions just a few years back. Again, this is industrial strength software, and it's actually used for chemistry in silica, but they also have educational resources. And like I said, if you're trying to explore carbon-carbon bond forming reaction, don't try and do that at home. But that is something that you can do in silica with great success. All right. In terms of the take-home lab kits, this is where we put it up a notch. Like I said, I love simulation. Simulation and real experiments with virtual equipment can really help folks see things that you couldn't see in another way. Get down to that level of atoms and molecules and understand things. And I think many of these experiments are just as valuable as traditional experiments we do in the lab. That being said, you don't know chemistry till you get your hands wet. Bottom line is going through and exploring and trying to understand, trying to do the experiments, see what doesn't work, see where the limits of theory are. That's something you got to get your hands wet. And I encourage you to roll into your total solution some take-home lab kits. Now, we looked at a bunch of different kits. We looked at some places where a company offered us a complete package and said, here it is, here's all the experiments, just fit these into your curriculum. That didn't work out too well. For one thing, some of the experiments would be a little bit deeper and others a little bit lighter. Also, they frequently didn't have enough experiments to get us through a whole semester. So we went to a company. We went to a company called. Oops, one more. We went to a company called Hands-On Labs. They're the #1 vendor for these lab kits in the nation. And I think they just acquired the #2 company as well. Anyway, they have a wide selection of lab kits. They have them for general chemistry. They certainly have them for intro chemistry. They have some for GOB chemistry. I don't think I wouldn't try and do a second semester organic with these at this point, but I think that's on everybody's radar. I think that's something people are trying to figure out how to make it work. Anyway, the advantage of the lab kits is, when I first started doing this, I started doing this before the COVID thing happened. I had one student who had a compromised immune system. She said she tried to take the course in a laboratory, and her doctor told her she couldn't do it anymore. She hit a roadblock. Had another student who wrote me a very compelling email. He said, you know, I'm not your average student. I've got 3 kids. I got a full-time job. I just can't cut off these hours. But I want to learn. I want to get past the bottleneck that is general chemistry and continue in my program, because whether you're doing biology or physics or engineering, you all start with general chemistry. Anyway, so our solution was to look at these lab kits, which have industrial strength experiments. These are more rigorous experiments, and we are asking students to do these outside of the university, outside of the college. And someone mentioned liability. There is an issue with liability there. As you start involving more concentrated or stronger reagents, as you start using more equipment, more glassware, there are liability considerations. That being said, the solution, yeah, eScience is not bad. We worked with, I looked at them for a while there. The one I like a little bit better is Hands-On Labs. Hands-On Labs, their lab kits come with $1 million indemnity policy. And more important than the fact that they're going to protect you from a lawsuit, they also have proper scaffolding to really help the students work on these experiments on their own time, on their own time scale. So, for example, there are pre-labs with the videos that will guide you through there. I know all of you guys want to build your own pre-lab videos, and we want to talk to our students and work with them. But I mean, the simple fact is, with load, building that whole program is going to take years. But a lot of this is done through hands-on. And when the students produce the reports, I mean, I tell students, you know, you're not handing in a lab. The lab is a place. It's where you go. Lab isn't something you do. It isn't something you read. It isn't something you hand in. You're talking about a description, a report. The experimental report, though, is really where it all comes together, where they can look at the results, put things together, and see things. And you want to be able to take a look at this report in detail. One of the things I like about this particular system is it comes with its own LMS, which integrates directly into Canvas through single sign-on and grade sync. You can move directly into the HOL cloud by clicking on a link in Canvas, and it'll bring you through. And when you look at the reports, you have granularity. There are challenges in building the reports. There's scaffolding prior to the experiment, scaffolding as they do the experiment, scaffolding coming out. But you can see each piece, and you can move through these reports very quickly. What I got on the screen here is an example of data that they show as possible data in a kinetics experiment. And then underneath it is the data the student put up there. This student used a spreadsheet to produce his own data. Other students might use paper and ruler. But you get to see each point in the lab, and you can process these experiments very quickly. Anyway, I'm a big fan of Hands-On Labs, so I wanted to give you their information. It's just holscience.com. I've been working with them for a couple years now. And one of the nice things is, again, you can build your own kits. I think, like someone else mentioned, there are some challenges with regard to logistics right now, building all these things. So they might be a little bit slower for build your own kits, but that's a solution. Now, I'll be frank with you, though. The disclaimer is the cost. The cost of these pre-built kits. I mean, you know, the old solution is you can do it yourself or you can pay someone else. If you pay someone else, it gets expensive. What we did was we set it up through inclusive access in the bookstore so students could purchase the kits there. We also were able to put in some matching grant money to reduce the cost on this. but that is one of the challenges. The next thing I wanted to talk about is remote participation. One of the things that we're looking at right now is, as we're moving into this environment where more and more students, either through HyFlex or through remote learning, are not going to be in the lab all the time. We still want to give them the flavor and the taste and the experience of an online of a professional chemistry lab. Remote participation is something that took off about 3-4 years ago. There's been a number of NSF grants for this, and the idea is this: you set up cameras and instrumentation in the laboratory, and students can access these experiments remotely. Now, this gets a lot more mileage in terms of electrical engineering in other forms, but there are chemistry labs all over the country, and there are, and I think this is something that's going to go forward, where folks are setting up experiments that you can participate in remotely. Now, we're looking at this on a much smaller scale. The scale, like I said, other folks have already done this. Circle, NIU, a few other places have set up these labs where folks can dial in and interact with experiments over the internet, walk into a real laboratory through a virtual door. This is great for spectroscopy. When you folks were in school, you probably had to dial in at midnight sometimes to get access to certain equipment through robotics and other forms. That's more the case here. But what we're looking at, and here are a number of institutions that offer dial-in or remote participation experiments. I think the iLabs one at MIT has since shut down, but my guess is as we progress farther with COVID, there's going to be more of this going on. But my view on this with the remote labs is that we can, instructors or proxies can set up and do experiments in the laboratory. We can have participation through remote instruction, where folks are able to get involved in real time, do real experiments, answer questions, see mistakes, and it can bring to life a lot of the vibrancy, a lot of the color, a lot of the realism that is in a laboratory. Now, we have the advantage of our labs are already wired with instruments for capturing data with various probes, temperature probes, pH probes, drop counters, etc. And we have the ability to put this data up on the internet, which means students can participate in the lab and capture their own data as you are walking through the experiment. We could also do this with HyFlex groups, where half the students are there in person and half are there virtually, and alternate as we go forward. But this is a fourth piece that we're exploring. We're just getting started with it.
Nick, do you have URLs? Do you have your URLs for the remote labs?
I do. These are various URLs. The big one was iLabs, and they had a lot of stuff going on. However, they've shut down about a year ago. There are other ones going on. This is still very new. You kind of got to knock on doors and kind of make things work. But there are 8 institutions that are offering this. And like I said, I think for chemistry, I think it's going to be more about, or potentially could be more about scheduled or interacting with real labs, where you have either an instructor or a student aide conducting the experiment, but then students participating or getting involved in it through Zoom and being able to capture their own data. And this is kind of what we're exploring at the moment. MeasureNet is a cool company if you want to get wired to allow your data to go on the internet.
Couple of questions now, or would you like to?
Yeah, hit me with your questions. I am happy. I don't promise answers, but I will do my best.
There you go. And a lot of answers are coming in the chat. This is perfect.
Nice.
this goes back a few slides. How is grading done? How do you do grading with the online labs and simulations? How do you work that process and feedback to the student?
Okay, so with regard to grading, the so it depends on, so there's different models there. With the hands-on labs, I set up in advance there's certain questions. There's part of the pre-lab, there's part of the post-lab, there's experimental data, there's certain videos or pictures the student has to capture and show to demonstrate their work. I assign point values to all of those, and this is what I like about hands-on labs. When the lab is complete, I can go in and I can rapidly see, I can go over one part of the lab. It's kind of like testing an exam, right? You like to grade the first question on all the exams and then the second question on the exams. With hands-on labs, you can do that with lab reports. You can see, you know, the question of the first one, and you can see patterns or trends in that, assign points to that. You burn through the labs, and then at the end you have a lab score in HOL Cloud. Now you can either set HOL Cloud up to through LTI to do grade sync with Canvas. I know pretty much everybody is using Canvas, or you can do an export-import model. But in that way, you can get your student data into Canvas. With labs in general, I don't think of them so much as a. I think of them more as a learning experience. They're more for the students to try things, experiment, and I want them to be brave. I want them to take risks. I want them to try new things. I want them to put out the answer, and so. I'm a little bit lighter on the grading of some of the labs. I don't care too much about spelling mistakes. I figure going down the line, they're going to learn how to make professional reports in the future. But with all of these labs, I think it's important to break it into pieces. You know, keep separate the data collection, talk about the quality of the data, give points for the quality of the data. Separately, talk about the interpretation of the data. Finally, what are your subsequent conclusions? I always, for every lab across the board, I always start with a question. You're here for a purpose. What question are you trying to answer? And then this whole process of experimentation is about answering that. Did that help? Was that a reasonable response?
Yes, I think so. Here's another. When you use lab kits, do you ever run the labs synchronously with students, say via Zoom, or is it all done, they do it and then later report?
Yeah, unfortunately, I have not done them synchronously with students. I'm hoping, that's kind of what I'm going after with the remote participation. But there are scheduling issues, but I'm hoping that, for example, with remote participation, since all of our lab benches are wired with this, we could have either TAs at each lab bench, or like I said, as we start opening up the campuses and have to keep social distancing, we could have a few students come in at each lab bench and then alternate, but the other half or the other 2/3 of the class could participate through remote participation. And I think that might give it more of the real time, you know, the instructor can still be there to give feedback, to answer questions, to work with them in real time. And I think that's something valuable and something I want to explore. But no, for lab kits, I talk to them in advance. I get emails at 2 in the morning and stuff, and I do my best to answer them when I can. But no, I'm not right there with them. And that's another reason why I like the hands-on labs. The hands-on labs provides a whole LMS that's associated with the lab experience that provides a lot of that scaffolding that unfortunately I cannot offer.
Very good. And we know the more the synchronous events are required, the more it's difficult for those very students who can't come to a on-campus lab experience because they've got family and kids and work and all that. Another question about the remote labs. Does that require a license fee, or are those free OER?
So all of the ones that I've seen, they're just getting started. They got big federal grants to do this, by the way. So all the ones I've seen so far, all you had to do was ask for access, and they gave you the access, and they said, in exchange, tell us what you think, share your data with us. this stuff is just getting started. And so it's going to, a lot of this stuff like spectroscopy in this, you're not going to see a lot of commercial companies getting into this because they're going to have to buy $1 million NMR or, you know, all this equipment. On the other hand, I can see universities as they're looking for other revenue sources to start increasing, you know, this and make this as an offering. So I do think there will be a way to pay money to get more access with more money, but I think I think it's not going to be the same challenge we see with a lot of other commercial solutions because it's going to be coming from universities themselves.
Very good. We just have 3 minutes left. I have allowed all the participants to unmute themselves, and maybe if you raise your hand in the participants pane, I'll scan through and you can open your mic and ask a question. But there was one interesting question we had from Kelly that she loves how you shared your slides as a background and also using the webcam to see you. Is that a feature in Zoom? How do you do that?
Okay, so my background is also coding, so I'm a chemist, but I'm a programmer. This is something that's not built into Zoom. However, there are products you can use. I'm using something called a virtual camera, and I'm building the virtual camera with other software. You can use OBS Studio. We'll do this, and there's a bit of a learning curve there, but I think it's very effective because one of the things is teaching is a very personal thing. I mean, people learning is changing yourself, and you know, trusting someone to change you is not just about, you know, how good are they with this, how skilled are they? It's do they care? And I think you have to see the person in the eye to really know, to really make that connection. So as we're starting to do more and more online, as we're starting to meet our students in virtual spaces, I think it's very important to be able to get to do more than just chat to make that communication. And so I'm playing with a lot of these visualizations.
Here's a question that I know has several layers to it. How effective do you feel these solutions are for students to actually learn chemistry? And we didn't address this earlier, but do you see these more as solutions for general ed, for the business major, for the English major who needs their science lab, or can chem majors effectively learn chemistry through these solutions?
There was a time when, you know, cell phones were for millionaires, right? You know, doing this cell phone, and it was clumsy and it was clunky, and the guy who pulled the cell phone out that looked like a small book, everyone kind of thought he was wasting his money and making but as technology moved forward, it got to the point where it was supporting more and more and more people. I absolutely think that the objective in chemistry is to understand chemistry. Yes, there are skills, but how to hold a pipette is really not the most important thing someone gets out of general chemistry or organic chemistry. And I think the underlying concepts, I think they absolutely can be taught in a virtual classroom. That being said, we got to let the technology catch up to the more intricate models that we are trying to share. Right now, you can absolutely do chemistry for poets, business majors, and lawyers. You can absolutely do that through virtual chemistry, you know, kitchen safe experiments, and so forth. We are now at the point where we can absolutely do this for STEM majors. General chemistry, I've been teaching general chemistry online for about 3 years, and I've been doing a face-to-face exam at the end of each of my courses, and I compared those exams in the student performance to the same exams, in some cases, I used for the last 10 years. And yeah, I can get retention, I can get completion, we can absolutely teach general chemistry online. Organic chemistry, that's the next challenge. And like I said, I wouldn't try and do carbon-carbon bond forming reactions in your kitchen right now. You know, you've got volatility of solvents, you have, there's a lot of challenges to that. Right now, we can't do it. But, you know, as we go forward, I have strong confidence we will be able to do it. We're just not quite there yet. But those of you who need to challenge to do organic chemistry now, think about molecular simulations. Look at programs like Macromodel, Spartan. Look at these ways of exploring the fundamental and the underlying principles of organic chemistry in silico. The solutions are available to you out there. It's just going to take a little bit of work to connect all the pieces.
Okay, Nick, thank you. And thank you, Mark. We have to close this off, but if you have any more questions, feel free to send them to me and I'll forward them to Nick and Mark. We will share this presentation afterward, both as a video archive, and I hope that Nick and Mark will be willing to share their slides with you as well. A little point, if you don't know, we had lots of great solutions in the chat as well from the rest of you. If you want to download those, because I'm not sure they'll automatically pop up when we finish, you can open up the chat window, and near the bottom on the right, there's 3 horizontal buttons. Click on that, and you'll see a save chat option, and you can do that to save the chat and take home those solutions. So thank you. I'll give you time to do that. I'm going to stop recording, but thanks to both of our presenters.